Good morning. Can you hear me? Would
Yeah.
one of you, yeah, I want to make sure I can hear you.
Hello, hello.
Okay, good. Just don't want, I've had these problems and weird problems in the past. Just want to make sure we're okay. Well, I want to welcome you all to the last class with the new material of the semester. We will have a class, well, let me just proceed here. We will have a class on Tuesday, but the Tuesday class is a review. There will not be new material in it. I was going to try and go over material from the whole semester. So if over the semester from any of the examples we did in class, or any of the practice problems we did, or any of the things that were done in the video lectures, the video recorded lectures, or any of the questions on the homework, send them to me via Piazza. Send your questions and make it clear so I can figure out which question it is. Like if it was homework 3, problem 7 or something like that, and what you didn't understand. And I will try and go over the material and do as many of these problems as I can on Tuesday. Okay. Also, I want to remind you, the final exam is a week from tomorrow. It's from 10:30 to 12:30. It is not the regular class time. The time is mandated by the university. I can't change it. This is a matching problem. What's a matching problem? Well, it's one of the things we're going to talk about today. But it's a problem that basically we have all the students in the university and they're taking a bunch of classes, and they try and set up final exams so that no student will have 2 final exams during the same time. And think about all the classes in the university and all the issues that involves, and all the classes people are taking. And so that's a graph problem. These are big computer science problems, and that's one of them that occur. And graph theory is one of the mechanisms for trying to figure out how to solve this problem. Okay, so that problem there is called a matching problem. And there are lots of algorithms that try and look at the matching problem, some less optimal, some faster, whatever. But graphs are a big thing in computer science. Okay, so we are going to hold special office hours next week. So Monday and Tuesday is regular. Okay, that's because that's the regular day. Apparently Wednesday is what they call it, a reading day or something. So there are no exams that I know of on Wednesday, but we're going to try and set up office hours so that any questions you have that you want help with while you're studying, you can come and ask one of the people whose office hours it is for help. Okay. Do not hesitate to ask for help. This is the last chance. Thursday is the first day of finals, and we're going to have extra office hours then too, but it has to work around people's schedules because they have finals too, the TAs, and I have other meetings scheduled. So we're going to have them. I'm in the process of trying to get them scheduled this week, and they will be online in the calendar, and there will be announcements next week. And on Tuesday, I'll do an announcement in class telling you what the rest of the office hours are. Let's see. There will be a bonus homework 8. And you say, well, what is that? And last semester they tried something. The university really wants you guys to fill out. Guys is a gender inspecific term the way I use it. Okay, it's like they and them. It doesn't tell anything about gender. It is a way to get you to fill out the class evaluations. And I understand they're a little different this time, and I don't have it set up. It supposedly is simpler, will take you less time. And I want you to fill out, I mean, I encourage you to do the class evaluations, however they're supposed to be done. And in order to, oh, you know, what do they say? They want places to, workplaces to give people paid time off to go get a vaccination. I'm going to give you paid points off, so paid points in addition to get you to fill out the evaluations. So right now, I have it set, although it is subject to some change, at 1 point on your GPA for this class. Okay, so if you have a grade, for example, if your average works out to be 92 and you fill out the evaluation, and there's a way to provide proof that you filled it out, and we'll go into that. If you fill out the evaluation, that will up your grade to a 93. So you go from A- to an A just doing the class evaluation. So that's my incentive to get you folks to do it. Okay. No, I mean, what, I'm sorry. You think what, okay. So the issue here, when I say 1 point, I take your scores from the whole semester and I figure out, you know, when we say the final exam is worth, the quizzes, 4 of the 5 quizzes are worth 60 points. That's 15 points apiece on the final. What happens is whatever grade you got on those exams, what we do is we take them, and suppose the best 4 out of 5 grades you got comes out to be, let's say, an 86, okay, the average. And then we multiply that by 0.6. And so your quizzes will contribute 86 times 0.6 to your final grade based on a score of 100 points. The final exam contributes 20 points, but it's not a 20-point exam. It's a 100-point exam like all the others. But we take your final grade on the final exam, multiply it by 0.2, and it contributes 20. And then we add up all of those scores, and that is your percent, your final point total for your grade. So if that comes out to be a 92.05 or something like that, then filling out the class evaluation will give you a 93.05, and you're an A instead of an A-. Okay. Now, if your score is a 90, it'll only move you to a 91. You're still in the A- range. Okay. So this is particularly helpful to people who, after you take the final exam, their points are just, oh, golly gee, can't you up it a little? Can't you give me that extra? This is a way to get that extra, not asking for favors. Do it, okay? I hope you like the way I teach, but even if you don't, fill it out, okay? I want to learn and be helpful to you guys in the future teaching this class so that I try and do it right. And I like to listen to you, as I hope you've observed over the semester. Okay. So that's the bonus homework 8. There is no content in homework 8. It's just doing the evaluation. When you will be providing the proof that you did the evaluation, you will not show me any of the values that you plugged in. What it is just something to indicate that you're submitting it. And that's what I have to double check, because apparently this year the buttons and stuff are different. And the way you fill it out shows whether you've submitted it or not. So that's what I have to double check to make sure that we get it right. Okay? Good. Those are my announcements. Yes, you have a question.
Are we like submitting some sort of like a screenshot of that we like completed it, or is it just
yes?
And is that just like the final like report, like at the end there'll be some sort of page that we screenshot and submit on Canvas?
Yeah, it's not going to be in Canvas. We're going to have a submission in Gradescope. just the way we do for all your homework problems. So we have to set that up and make it available. If you've already done the evaluation, there has to be, I will figure out a way. And that's why I think this year it's different. I think there's a way of telling, and I have to look into it. So if you've already done the evaluation, you still can get the point. I just have to figure out how to make sure. Okay? There was one way that they used last semester, but apparently it's changed. They have a different kind of dashboard for you to look at or something. I don't know, but I have to verify that and look into it before I can put the instructions out for you. Okay? So if you filled it out, great. If you haven't, wait for my instructions and fill it out then. I'm giving you a window till the end of exam period, but that means I can't submit your grades until I know. So I might change the date that you should do it by, but I'll figure all that out by Tuesday. The instructions will be an announcement made in Canvas. Okay, so I will have it in class as an announcement, and it'll be an announcement via Canvas. So make sure you check Canvas. Okay? A new way to access the feedback area is through Canvas. Good. I will look through that. Okay? I'll try and figure it out. All right. Let's jump into chapter 7. So these are all definitions we've had before. And I want to remind you that a tree is a connected simple graph with no cycles. Okay? That's the big deal here. And a spanning tree, if you remember, is a tree in which every node in the graph is represented, okay? And a weighted spanning tree, well, you have to have a graph that has a weight associated with a numerical value along each edge, and then you get a minimal spanning tree. Now, minimal spanning trees are generally not unique, okay? But it means the definition of a minimal spanning tree is that no other spanning tree has smaller total weight. So you can have multiple spanning trees with the same lowest weight, and they're different. Okay? Isaac, if you're trying to talk, you're muted. Okay. So let me remind you that we had a spanning tree algorithm that was pretty simple, and we went through that example. Okay, what it says is for each I in one, you start with a simple graph and you say, as long as there's a cycle in the graph, choose an edge E in any cycle and form a subgraph of G by deleting that edge from the previous one. So every graph, the new graph, the higher subscript will have one less edge than the previous one, and you've broken one cycle. The final result is a spanning tree. Now, we were just starting to talk about Prim's algorithm, and that's it for a minimal spanning tree. And that looks at things totally different. What that one says is, given a connected simple graph, remember what simple is, no parallel edges, no loops. With n plus 1 nodes, you pick any node in the graph. So that tells you there's not going to be a unique minimal spanning tree, so because you can start with any node in the graph. And then you define a tree. You define it as the tree T, which has vertex V0 and no edges. Okay. Now we're going to create a new tree based on that, where VK is a set of nodes and EK is a set of edges. And the way we're going to pick that is we're going to start looking, let me call it AK, is the set of edges with one endpoint in EK minus 1 and the other endpoint not in EK minus 1, okay? Okay, so it's the set of edges with one endpoint in VK minus 1, so to speak, but the edge is not in EK minus 1. Okay. And then you set EK to the edge in AK with the smallest weight. So you look through all the edges with the smallest weight. And in case of a tie, which will exist frequently, you pick any edge with the smallest weight and let VK be the node that's not in capital VK. And then you create the new edge by just adding the new E that you've added, and you create the new node set by adding the vertex at the other end. And you just keep going. Okay, so there's a lemma that says for each K, TK is included in the minimal spanning tree of G. And then the big theorem that says the tree T sub n returned by Prim's algorithm is a minimal spanning tree for the weighted simple graph G. So let's do an example. Okay, that's my first thing. And I'm doing an example based on the same graph I used for doing the tree, the spanning tree, but this one's different. So now I've thrown weights on all the edges and I've given them integer weights just because it's easier to connect with. Okay, so on the left, I have the edge and then the cost of function associated with them. And then I show the graph with the cost functions associated with them. And then finally, I'm going to pick the first one. So I'm going to pick the edge. Well, I pick an edge here somewhere. So I think I pick, the V0 is the vertex G all by itself. Where's G? G's right here. G is there. So I pick that vertex, and remember, edge set has nothing in it. And then I look and say, well, I have to pick all the edges that have a vertex in V0. So there are only two edges. That's the edge from G to B and G to H. And if you look in the notation I have here, I label them with the weight as well, just because it's easier for the algorithm. So it's the weight BG that has, I'm sorry, the edge BG that has weight 1 and the edge GH that has weight 2. Well, BG costs less than GH, so that's the one that I put as E1. Okay, so I started with G, I now add B to the vertex set, and I add EG to the edge set. Okay, so what set is that? Let's see, I've added this edge. All right, what's the next step? There it shows it. So the next step says I have to form A2. What is A2? A2 is consists of the edges which have a vertex in V1, but the edges are not in E1. So what's that? Well, that would be, well, it still would be the edge GH that has value 2, because I just haven't used it. And H is not in the set. And it's whoever B connects with that isn't G. So it's BI, BC, and BA are the three edges that we add in. Okay. So here we are. They're the three new edges that we added in. And we look and see who's the lowest weight. Well, it's the edge AB has the lowest weight. Got it, weight 1. So we add the edge AB, we call it E2. And what vertex is that we're going to add? We're going to add the vertex A. Okay, so our edge set now is AB and BG. And we move on. So on my graphs here, I'm turning to red the ones that we're adding so you can follow along. So now what do we do? Well, now we have to form A3. So A3 are all the edges that are connected to either G, B, or A that are not in V2. So what are they? Well, it's BI, which was already in V2. It's GH, which was already in V2. it's BC, which was already in V2, but now I add AC, that wasn't in V2, and I add AD, that wasn't in V2, and so that becomes A3. Notice what we're doing is we're looking at the previous A set, and so far all we've been doing is adding to it, but you're going to discover that's not all we do. Sometimes we have to delete edges, and we'll get to that case. Okay, so who has the lowest value there? Well, we look and we see that AC has value 1. That's the lowest value. So we add the edge AC, we add the vertex C, and now we have the edge set with 3 edges in it, which shows up there. Notice this is the edge AC right here. Hard to see it because it's a short one the way I drew the graph, okay? Yeah, you missed a bunch of important announcements, but I can't go over them now. You can look at the notes at the end of the class or look at the video. Okay, so now we're going to solve for A4. So we look at A4 and we say, well, GH still isn't used. BI still isn't used. BC still isn't used. AD still isn't used, and CD still, we add CD. CD is a new one, okay? What happened to edge BC? Why is that no longer in A4? Well, it's no longer in A4 because both vertices, B and C, are already in V3. B and C are already in V3. So the edge BC is no longer in A4. So we have to remove it from A4.
Do you mean AC, the edge AC?
Yes. Did I say BC? I'm sorry. Yes, we're removing AC. This edge. I need to do it in blue. That edge gets removed. Okay? Thank you. I'm sorry for confusing you. Okay. So then we look and we see there are 4 edges that are all tied. There are 4 edges with value 2, with cost value 2. So we can pick any one of them. Okay, so I picked edge GH just because it's been there for the largest number of A's. Yes, AI is the value or the set of edge options for the next edge to add. And you have to look at them all and decide. And remember what you're doing, you're always picking edges that are connected to edges, to vertices you picked previously, but edges that have not been picked. And in this case, that edge, if I picked it, would form a loop, and we can't have loops in a tree. So that's why we have to remove that from contention. Okay, so I picked, for the heck of it, for no good reason, edge GH. Okay. So we add edge GH to E, and H is my new, there's H, that's my new vertex that I add. Grant, yes.
I'm a little confused in A4, or that the edge that you crossed out with the blue pen. You said that that one's not supposed to be in A4.
It is not.
Isn't that the BC?
Oh, wow.
It makes sense to me, but I'm confused. Okay.
That's because I was very tired when I did this. I apologize.
You're okay.
Right.
Thanks.
B and wait a minute. B and C are in V4. So AC is no longer a valid edge. So the words I said were right. And we cross it out. It's not there anymore. Thank you. Okay. Then we move on. So now what edges have we picked? Well, we have GH, GB, BA, and AC have already been picked. So now we look at all the edges that are connected to one of those vertices that are not in V4 and that would not form a loop if I added them in. So what do I have here? I already removed that. And so what we see here is, again, we have a bunch of edges that tie for the lowest cost. So we pick one, and I picked BI. Which one is BI? This one. Why did I pick it? It's been in the most A's. I want to give it a way out. Okay? And again, I add BI to the edge set. I add I to the vertex set. And we move on. Okay. Again. Wow, this guy doesn't wants to hang around a long time. Okay. All right. So now we're going to form A6. Okay. So everybody connected to any one of those vertices, that's no longer anyone connected to V5 that's not in E5. We look at, and if I did this right, I have AD, CD, FH, and IJ. Okay? And I have to pick one. So again, what did I pick? I picked AD, which is this edge. And we increase V by adding D. We increase E by adding GH, and we move on. We're getting there. Now we have A7. A7, well, goodness, thank goodness I removed this. So we have FH as a contender. Where's FH? FH is this edge. Let me do that in blue. We have FH. We have IJ. We have DF. Maybe. And DJ. Okay.
You highlighted FJ. I think you meant to highlight FH.
Yes, thank you. F. Where's FH? Yes. Thank you. Okay. So now we actually have one with the lowest cost, and that's DJ. So when there's only one, we pick it. We add the vertex J, we add DJ, and we have T7. Okay, now we form A8. What are our contenders for A8? Well, we have FH, which is this one. Is this blue? Blue. FH. We have DF. That's this guy. Or FJ. Okay, so there is a lowest cost. FJ has value 1. So we add FJ, we add the vertex F, and now we have T8. And that's our graph. That's it. That's our tree. So look, if you look carefully, you see there are no loops because we excluded all the edges that were possible loops from being contenders at every level. And we hit every vertex. We have edges going to or through every vertex. Okay? So, no, I'm not missing IJ. I don't need IJ. IJ would form a loop. We can't have IJ. But I go through the vertex I and I go through the vertex J. I'm sorry, would form a cycle, not a loop. I go through the vertices. Remember, being a spanning tree means that you have to go through each vertex, not through each edge. Okay? All right. Good enough. We have a practice problem here. I can't tell you the number of slides, time that took, and I didn't get it completely right. We have a practice problem. If G is a tree with nodes U and V that are different, and UV is not an edge in G, then adding an edge UV to G will form a graph with exactly one cycle. Okay? Practice problem. Give it a try. Give it a start try. What would be the first thing? It is not an induction. So we're going to use contraposition on this. Or I was going to use it, which is like contradiction. So we have a theorem almost for this. Thank you for recognizing that. That's going to be the first step in our proof. The first step in our proof says proposition (7.2.2) says there is at least one cycle in G prime. G prime is what we form by adding the edge UV to G. Okay, that's true. It forms a cycle. What we need to prove is that it's unique. Okay, the difference is we're not saying that it's nothing new to say there's a cycle. Trees by definitions have no cycles. Well, you say, is it the only cycle? Well, let's do a proof by contradiction and show that it's the only one. Okay, so what's the first thing we're going to say? We say one, any cycle in G prime includes UV. Why would that be? Because. Why would that be? That would be, otherwise, the edges of the cycle would be entirely in G. And we know that G has no cycles. Otherwise, the edges of the cycle are in G, but G has no cycles. So UV must be in any cycle in G prime. Okay, now how do we prove it's unique? Well, the way we prove it's unique is we use by, let's see, one of the practice problem, I don't know which one, from lecture 21. Any path, no, there is a unique path in G from between U, and V. Okay, that problem helps us with this because we now there's unique path. So now what we know is we know two things. We know that any cycle in G prime must include UV. So suppose there are two cycles in G prime. They include UV. Suppose two cycles in G prime, they both include the edge UV. Okay. So if we remove UV, we could form a new cycle let's say that starts at U. So we have two loops, okay? And here's the edge UV. So if I take out the edge UV, take that away. Okay, there's the edge. So if I take that edge away, then I can form a new cycle that goes loops around from U to V on one of those cycles that's in G prime and come back on the other cycle that's in G prime. But now all of those edges had to be in G because I only added one edge. That means I've made a cycle in G, which is impossible since G is a tree. But then all edges are in G. And that's a contradiction since G has no cycles. Okay, therefore, it forms a graph with exactly one cycle. Okay? Question, Britton.
Yeah, can we just assume that, so when we add the edge UV, that creates a cycle? We know that creates at least one cycle?
We
That's
know
by the
from
definition of
proposition 7.2.2 that it does. You're not assuming anything. You're saying you're quoting the proposition that says it's true.
So we're
So
allowed to just use that proposition is what, like.
Are
we
you
use that
asking if
on
you're
the
allowed to
test.
use it on the test, on the
Yes.
final?
Yes.
Good question. You are if I don't ask you to prove it on the final. So, you understand?
So you would probably give us some more information on the question, like.
Oh, you bet.
Assume.
On any final, I will allow you. Yes, I will try and make sure it's clear what you can use and can't use.
Okay, awesome. Thank you.
Okay, that's the key here, to be able to know that there's a unique path in a tree between any two vertices. That's important. Should I say it again? That's important. Okay, let's go on. We got lots to do today. Okay, what's an isomorphic graph? Well, the term iso means equal. It's from Greek meaning equal. And basically, the statement is two simple graphs, G and H, are isomorphic if there's a one-to-one, an onto function f that's supposed to be lowercase from the nodes of G to the nodes of H, such that an edge of UV is an edge in G if and only if f of U, f of V is an edge in H. And that function is called an isomorphism. What it means is that this function preserves structure. Okay, now when we look at graphs, we always make a visualization of it in our minds. And as we've seen, there are lots of ways to draw the same connections of a graph. Okay, many of us might draw them slightly differently. We'll put the vertices in different positions and the edges, and it's still the same graph if it has only those edges, but it looks different in the visualization. And so this isomorphism is a way to say, are these two the same? Okay, has it preserved the structure? And the structure says you not only have to have a one-to-one mapping of the vertices, but you have to have a one-to-one mapping of the edges so that an edge is in the first graph if and only if it's in the second graph. Now, what does that mean? What does that imply? Okay, implies they have the same number of nodes, the same number of edges, because you can't have one-to-one mappings otherwise, the same number of nodes of any given degree, because you're mapping the edges across the same way, the same number of cycles, and the same number of cycles of any given size. Okay, remember, having any one or two or three of them does not make it isomorphic. The isomorphic comes from this structure. These are a consequence of being isomorphic, okay? This does not say if and only if. It says if they're isomorphic, then these things follow, okay? I'm sorry, someone said, I thought we contradiction, contrapositive. I'm sorry, I mentally put them in the same category, even though I know they're not the same, okay? We did not do contrapositive, we did contradiction. Okay, what we said is assume that there are two cycles in G prime, which is the contradiction. So I apologize. Okay, so we have a bunch of graphs here. Tell me which two are isomorphic. And are there more than two that are isomorphic? I don't have labels on them. I just have structure here.
The one in the top middle and the bottom left.
Top, middle, and bottom left. Good. What do we have? We have every vertex has degree 2. What were our rules? Every vertex has degree 2. That we have the same number of cycles, namely 1. We have the same number of edges, same number of vertices, and the same number of cycles of any size. Namely, we have 1 cycle of length 4. Good. That's a consequence. Are they the only two? All these graphs had 4 vertices. Yes, Britton.
So you're saying that those properties are a consequence of it being isomorphic. Just looking at this picture, then how would we determine that they're isomorphic before we like go and say those properties? That makes sense.
Well, what I would do, remember the statement that they're isomorphic if I have a mapping between the vertices and a mapping between the edges that are if and only if. So for example, I would take this vertex, I call it number 1, and I'm going to map it to that one. And I'm going to take this vertex, number 2, and I can map it to any of the 3 remaining ones. Any of the 3 remaining ones. Which one would you like me to map it to? Let me map it here. I'm going to take this one, call it 3, and then I'm going to map it to, let's say, here. And I'm going to take this one, call it 4, and map it here. Now, can you see a simple transformation that I take the first graph and I lay 1 down on 1, 2 down on 2, 4 down on 4, and 3 down on 3, and I haven't changed the structure. The edge structure is the same. I have an edge 1, 4 that connects to an edge 1, 4. I have an edge 2, 3 that connects to, an edge 1, 3 that connects to an edge 1, 3 here. I have an edge 1, 2 that connects to 1, 2 here. And those are the only edges. I have no cycles in either graph. The structure is preserved. Okay? What that means is I could take the graph on the left and wiggle and twist without changing any edges. Just wiggle and twist it around and get the one on the right. Okay? So, for example, I would take this one, map it here, and at that point, I have something that looks like this sticking up. Okay, but what I have is 2, 3, and 4. But that doesn't match. So what I have to do is take this one and turn it so I have something that looks like that, if I could do it myself, and then that matches. So I rotate, translate, and rotate, and I get the same graph. And that's called a rigid body transformation. Okay, but it doesn't have to be rigid body because the angles aren't the same. Rigid body means the angles are the same, but you get the idea, I hope. Okay. Oop. Did we get them all? Yeah, this last little guy isn't related to anyone because why? It's not even simple. Is it simple? Yeah, it's simple. There's only one edge, at most one edge. Okay. There's at most one edge. It has no loops, no parallel edges. It's not connected though. Is 5 isomorphic? Yes, every graph is always isomorphic to itself. Okay, let's go on. So we have different types of graphs. We have planar graphs. A planar graph is a simple graph in which there's a way to draw it in the plane so that no edges cross each other. Now, it doesn't mean you know how to draw it that way. It means that it can be drawn that way. Okay, so that makes it hard because you can scratch your head for a long time and say, I don't know how. Okay, but if someone can do it that way, then it's called a planar graph. A drawing of the planar graph in the plane so that no edges cross each other is called an embedding. For a planar graph embedded in the plane, the face of a graph is a region of the plane created by the drawing. Okay, so if I look at that graph, okay, and label the edges 1, 2, 3, 4. I have 4 vertices. What are the faces of that? Well, I have 1, 2, 4 is a face, 2, 3, 4 is a face, and 1, 2, 3, 4, the infinite, that's the infinite face. Okay, we're going to look at that. Okay, we're going to look at that. All right. Okay, and a graph is called bipartite if S is a set of, set of nodes can be partitioned into 2 disjoint sets, S1 and S2. So every edge has one endpoint in S1 and one endpoint in S2. Okay. Now that is something, bipartite graphs arrive as matching problems. Okay. You can think of the simple case where you have the set of nodes equal all the students at the U and all the classes at the U. And the matching problem is to match each student with the courses they take. So you have the set of students and the set of courses. Okay. A complete graph on n nodes, denoted by a case of n, is a simple graph, no loops, no multiple edges, with nodes 1 through n that has an edge between every pair of distinct nodes. By definition, a simple graph is always connected because every pair of nodes has a path of length 1, the edge between them. Okay? A complete bipartite graph on n comma m nodes, where n is the number of nodes in the first set, S1, and m is the number of nodes in the second set, called K and NM, is a simple bipartite graph with nodes S1 from A1 to AN and S2 from B1 to BM, with edges connecting every node in S1 to every node in S2. So for example, I think I have this as an example here. So this is a bipartite graph. There are no edges between the vertices in S1 and no edges between the vertices in S2, but every edge in S1 is connected to every edge in S2. Okay, that's the definition of a bipartite, complete bipartite graph. Okay? Okay, so here's our example. Show these graphs are planar by drawing an embedding. So we have an example of K4, and we have an example of K32. And then we have an example of the cube. That's a harder one. That's a line drawing of the edges of a cube. And that's a graph. I'm connecting them up. It has 8 vertices and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. I don't know what a dense graph is. I'm sorry. I know that it's fine. So look at what we have here. How would I turn that graph into one that has no edges crossing each other? Very good. So the man says, hold it up again. I want to make sure it's exactly the same. The man says, do that. That's exactly right. What are their faces? Let me label them. 2, 3, 1, 4. So what are their faces? Well, I have a face 1, 2, 3, back to 1. So that's one face. I have a face 1, 3, 4, back to 1. That's a face. I have a face, well, here's another face, 1, 4, 3, 1, 3, 4, if you like, over here. Oops, I have that's wrong. I don't have that. It's connecting 2 and 4. Thank you. So these two are still the same, but I have the face 2, 3, 4 back to 2, that one. And what are the edges of the infinite face? That would be 1, 2, 4, 1, 2, 4, 1. And that's the stuff out here, the edges of the infinite face. Okay. What about this complete bipartite graph 3, 2? How do we do that? Has anyone got any thoughts? Okay. Well, what do you think we can do? Maybe I'll leave that for you to think about. Let's talk about the cube. How are we going to do that? Oh, did you have an idea? I'll do it. Which is which? Which vertices are in which set? You have to label them so I can tell. Okay, we have A, B, C. It's what, okay. So the man says, take this one and come around to there and take, which one have you done? What have you moved around here? A, B, C. We have A to X. So we're going to go A. Oops, I did that. I did not get what you have. Let me do this one. We have A to Y. A to Y coming around the bend here, A to Y, and we have B to Y. We leave this one intact. We remove this one and go B to Y, and we took out this one. That's gone. So we take those away and we redraw them. Okay, good job. What do we do with the cube? Expand and translate, the man says. Which one is it? E, G, F, H. Yeah, you can do this. So you have C, D, A, B, E, F, G, H. Good job. Good job. Okay, you got it. Let's go on. Show that each of 5 houses can be connected to 2 utilities without their lines crossing. And then for how big a value of n is kn2 planar? In other words, how can we do it without crossing? So I have 5 houses. I'm not even going to draw it for you. Well, I'll draw it for you. So I have my houses in red, 1, 2, 3, 4, 5. And I have my 2 utilities in blue. How can I draw it? So I think I'll do this one because we're getting low on time. So I'll draw it differently. So let me draw 1, 2, 3, 4, 5, and then the 2 utilities are here. Okay. Now I can do it. I just 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. How many can I go? How big can n be? As big as you want. We just keep going out along that line and we don't have to have edges crossing each other. Cool, huh? Okay. So it says the complete graph on 5 edges, on 5 nodes is not planar, and the complete bipartite graph 3, 3 is not planar. Are we allowed to move matrices while doing these embeddings? I don't know what moving matrices are here. Remember, we're just move vertices. Absolutely. Absolutely. Remember, vertices aren't fixed in graphs. Graphs are a visualization of a bunch of connections to each other so we can work with them and make sense out of them. Okay? Okay, so there's some really important stuff here. Given an embedding of a graph in the plane, if you remove an edge from any cycle in the graph, you decrease by 1 the number of faces in the graph. And every edge on a cycle in a graph borders exactly 2 faces. Now, this is important. And why is this stuff important? Well, the next theorem that comes up, Euler's theorem, is the basis of a lot of what's called a lot of analysis of solids in solid modeling and in a lot of computational geometry, okay? That the number of vertices, given a planar graph, connected planar graph, that's the biggie, embedded in the plane. So now you've drawn it so that there are no crossing edges. Then it says the number of vertices plus the number of faces, where you're using V and F instead of as sets to indicate the number, equals the number of edges plus 2. Okay? So remember the complete graph on 4 points. We looked at there. So we had 4 vertices. How many faces did we have? We had 1, 2, 3. Don't forget the infinite face, 4. How many edges do we have? 6 plus 2. Now, if you have a graph that doesn't have that, if I had drawn the graph like this, it would not look embedded in the plane because those cross each other. But the faces, you have to be careful there. That has to do with the infinite face. Okay? And so we look at that and we say, aha. If I have a graph that's planar, I know something about it. Okay. Let G be a planar graph in which every edge is on a cycle, and let F be a face created by an embedding of G in the plane. Remember, the embedding means no edges cross each other. The size of F is defined to be the number of edges on the cycles in G that makes up the boundary of E. That makes up the boundary of the infinite face. Okay? Boundary of F, I'm sorry. Boundary of F. The boundary of F are the edges of the infinite face. Okay. And at a planar graph in which every edge is on a cycle, the sum of the face sizes is twice the number of edges in the graph. The sum of the face sizes, remember the face sizes are the number of edges in the cycle that define it. And then in any planar graph G in which every edge is on a cycle, if K is the size of the smallest cycle, then the number of edges in G is at least K over 2 times the number of faces in G. And you say, bah, what's this about? I'm going to tell you the next problem we're going to do is this one. And you can think about it during our break. Right now. Then we'll resume. I'm sorry I went a little long. If you have any questions, now's the time. Actually, I'm not going to do this in class. I need to get to the last part that's important. Let me tell you that in order to prove this problem, you need to use these 2 characteristics, okay? Because it's a simple connected planar graph and every edge is on a cycle. So that says, then you know this, and you know this, and you know Euler's formula holds. Okay, and those are all the key to proving that. Is this the one you wanted to go back to? Okay. I can't take away your break now, but I'm going to skip it. This proof. Is it okay if I proceed to the practice problem? Okay. So I'm going to skip this and leave it for you. Maybe I'll ask to be done in discussion. How's that? I'll send a note to the TAs to do it in discussion tomorrow. Meanwhile, this is the most fun thing we've had in a while to talk about. Okay. Adjacencies are a way of combining things about graphs into linear algebra and learning about the graph structure by using the algebra. So it's a connection between them, and it's really fun. Some of you may not have learned how to multiply matrices, and we're going to briefly talk about that here so that you get the idea. Okay, so given a graph G with a set of vertices, n vertices, and an edge set, the adjacency matrix of G is defined as the n by n matrix M, whose entries are the natural numbers that tell you in the ith row and jth column, written, we write ij, I comma j, called mij, the number of edges connecting vi to vj. Okay, now in a simple graph, that value is at most 1 because there are no edges. I'm sorry, there are no parallel edges and no loops. Further, in a simple graph, the ii element, mii, equals 0 in a simple graph. Why? Somebody unmute and tell me why.
There are no cycles in a simple graph.
Perfect. There are no loops in a simple graph. So a loop would go from I to I, vertex I to vertex I, and we don't have any. So MII is 0 in a simple graph. And in a simple graph, the ij element is at most 1. There's at most 1 edge between any two vertices. Okay, so you immediately learn about structure of graphs from just looking at the values in the adjacency matrix. If the graph is directed, then the ith row jth column element called Mij is the number of edges from vertex I to vertex j. Okay, this is an ordered pair. In an undirected graph, you have the same number of edges. Mij is the same as Mji because we're only counting the degree between the two. Are there multiples or there whatever? In a directed graph, Mij may be quite different than Mji. Okay, let's do one. Consider the graph G with vertices v1, 2, 3, 4 and edges v1, 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 v2, v1, v3, v1, v4, and the directed graph H on the same vertex set with edges v1, 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 v2, v1, v3, v1, v4. Okay, so we've listed the same, we've listed them looking the same, but one is an ordered pair and one is just an undirected edge. So what's the adjacency graph of G? Well, let's figure it out. So this is M of G, let me say, write it that way. And let's see, there's a loop from 1 to 1, so the 1, 1 element. Okay, let's see, there's an edge between V1 and V2. So, and that means there's an edge between V2 and V1. There is no edge between V2 and V2. There's an edge between V1 and V3, and V3 and V1. There is no edge between V3 and V2. There is no edge between V2 and V3. There is no edge between V3 and V3. Where else are we here? There's an edge from V1 to V4. and an edge from V4 to V1. And I think we just filled in, that's it. So what's the graph of G look like? What does a graph of G look like? Well, if that's 1, 2, 3, 4, it means I have a loop at 1, and I have an edge between 1 and 2, 1 and 3, and 1 and 4. So if I give you the graph, you can do the incidence matrix. If I give you the edge list, you can do the graph. You can do, all of these representations are the same. Okay? The easiest ones to understand for me, I can't tell you, are both the visualization of the graph and the adjacency matrix. What's the adjacency matrix of H? Well, let's draw the graph of H. We know there's a loop from 1 to 1. And then we have 2, 3, 4. So we have all these edges emanating from 1 out. Okay? So what does our M of the H look like? What is that? Well, I have 1 to 1, 1 to 2, 2 to 1 to 3, 1 to 4. Do I have any other edges? Nope. Okay. The number of ones in this graph have to equal the number of edges. Okay, Britton, yes.
Do the rows always represent the vertex from which the edge is
Yes.
coming from in a directed graph?
Yes.
So it needs to always be that direction.
Yes.
Thanks.
There might be some world in which it isn't, but not this one. You'll see why in a minute. Okay? All right. So here's some cool stuff about adjacency matrices. It turns out that if a graph represents some relation, remember, we can make a relation. It's just the set E's are the relation from and to. On a set of nodes V, and M is the graph's adjacency matrix, then the graph of the composition, M squared, is the matrix M multiplied by the matrix M, and it represents the adjacency graph of the composition of R with itself. Similarly, in general, if you have two relations and you want to compose them, you end up multiplying their adjacency graphs, and then you get the answers of what are the edges in the composed graph. So how's matrix multiplication done for people who don't know how? That's it. What we do, this is the algebra definition of it. This is what happens. To create the 1, 1 element of the product, we take, this is an undirected graph, so it's symmetric. We take the row of the one on the left with the column of the one on the right. So if we want the 1, 1 element in the product, we take the first row of the first matrix and the second row of the first column of the second matrix. We add each of the elements, multiply each of the elements together, and then add the product up. And that's what's being done in that figure. And then we put it in the 1, 1 position. Here, we want to find the element in the 1, 2, 3. This is, we're looking for the fourth row, third column of the product. So we take the fourth row, the third column, multiply element by element together and add them all up. Okay. And that's matrix multiplication. Okay, this is cool. So given this adjacency matrix, it's a little different than the last one. What is m squared? What is m cubed? Okay, I don't have time to do it, but did I include this one in the slides I put out for you? If not, I'll try and add that. Why is that important? Why is knowing the cubed important? Well, if you want to represent walks of length k, and this is either directed or undirected graphs, it doesn't matter. We have a theorem that says if M is the adjacency matrix of a directed graph, I guess this one is directed only, but we don't need it to be for some work. Well, on the vertices from 1 to n, the row I column jth entry of m to the k multiplied m times m times m k times is the number of k step, k edge walks from node I to node j in graph G. Okay, so this is the number of walks of length 1. That is the number of edges. This is the number of walks of length 2. That's the number of walks of length 3. So what are we doing adding them together? We're counting the number of walks from node I to node j in the graph of length 1 or length 2 or up to length k. Remember, plus is an or. Okay, so we don't care if it's 1, 2, 3. We're just saying how many are there of any length up to k. So we add them together after we multiply them. So the last important thing is when we have a relation, we can do the adjacency matrix of the relation. Okay, and that is the same thing. That's like a directed edge, the same way. And so if AB is in the relation, then row that corresponds to A, column that corresponds to B is a 1. Adjacency matrices for relations are always either 0 or 1s. That says, is there a relation between A and B or not? Okay, and you have a partial order defined on the matrices by saying that one matrix is less than the other if they're the same size, and element by element, one is less than the other. So that means if they are adjacency matrices of relations, if Mij is less than Nij for all ij, what can it be? Well, Mij can be 1 or 0 and Nij can be 1 or 0. So what that says is if N is a 1, then M can be 0 or 1. If M is a 1, then it means N is a 1. It's bigger. It can't be smaller. Okay. And I'm going to, you have these in the notes. These are the really important things for everyone. What it says is there are a couple of things to say. Okay. What it has to do with is a matrix is, a relation is transitive if M squared is less than M. So if there's an edge from A to B and an edge from A to C, then M squared has a 1 and N has a 1 because it has to have a 1 in that position if it's transitive. If there's no edge from B to C, then it's got a 0 even if N had a 1 in there. Okay. So that's what that says. And I'm going to leave the last thing. That's a homework problem for you. And I'm sorry, but I went over 2 minutes. I'll make Tuesday 2 minutes shorter. You're free to go or ask me any questions you want. Class is done. Bye.
Hey, I was just gonna ask if you could go over the infinite side again real quick, or the infinite
what?
face. I mean, infinite face. Just will you go over that one more
The
time? I was a little
infinite
bit
face.
confused.
Yes,
Yeah.
yes, yes. That's back here. There. The infinite face. So what it means, remember in a planar graph, think about the cube, okay?
Yeah.
So what happens when we think about the cube, wherever that was? There, we think about the cube. So down here, I have a face, and I have a face G, H, D, C. Okay, I have a face G, H, D, C.
Yeah.
When I embed it in the plane, when I make it so no edges cross, that face, it's like I take it and I squeeze it out and it becomes infinite.
Let's see.
What
But
happens?
isn't that face like still there and like in the expansion to the right?
There's no boundary to it. The boundary to it is EFGA or EFHG.
Oh, I see. So it's okay. I think
It
I
still
get it
has
now.
the same boundary. So you look
Okay.
at it and say, well, when I squeezed it out, somehow I made it go to infinity. So there's something in mathematics. Let me give you an example. I can embed the cube on a sphere, okay, without any problem. I can make the top face be a latitude and the bottom face be a latitude and the four edges be four longitudes, right, that are spaced out around it.
Sure.
Okay, so if you look at the globe and you try and flatten it out, what happens? Well, what happens is an impossibility. You can't write it in the plane without stretching something to infinity. Namely, what you're doing is, say, taking the North Pole and saying, I'm cutting the world there and flattening it out. And the North Pole ends up so that it becomes a bigger and bigger circle and goes out to infinity.
Okay.
Okay, so that's what this kind of thing does.
Okay, that makes sense. So whenever you're counting these embedded graphs.
I actually, I'm sorry, I apologize. When I was doing, we have A, B, C, D, and this one is G, A, E, F, G, H that goes out to infinity. But yeah, you get the idea, right? I did it.
Yeah.
Okay.
So when we're counting faces, we count just any distinct like sets of areas, including outside the shape.
Including the infinite one.
Okay.
And if you have an edge that looks like this in a graph, this is still a face because there is no cycle here. That little guy is off by itself. It could be there, or it could be there, or it could be there, or it could be anywhere, any of the faces. Okay, so when you have a planar graph, not everything is on a cycle.
Okay.
And it's the cycles, okay, the enclosing areas, the smallest cycles that enclose an area, enclose, totally surround, okay?
Okay.
If you have a partial like this, ABCD is still, ABDC is still a face, okay?
Okay, yeah, that makes sense.
It's
Because
cool.
that
It is
extra
so
point
much fun,
isn't its
graph
own
theory,
thing.
and is so amazingly important,
Okay.
okay?
And then I had another question about adjacency matrices.
Yes.
Could you use those to determine whether or not a graph is isomorphic? Right? Was it isomorphic? Is that the? I think it's isomorphic, where you can sort of rearrange it, because, like hypothetically, you would have this matrix where you've just shifted columns and/or rows, right?
Yes.
All right. So, I guess what I'm asking is, like, I'm not that caught up on my linear algebra. I took the class, but kind of forgotten most of it. It's been a year now. But is there like a mathematical operation that will determine whether or not they are sort of equivalent matrices in that way, where you could shift rows and or columns?
Yeah, but it's a little beyond this class. I don't want to talk
Okay.
about that. Okay, but just think about it. The labeling, what you're doing, remember, is you're labeling vertices, which means you would be labeling row and column.
Okay.
Okay, so
makes
if you're saying one graph, the labels are VI and the other they're called WK. Okay, if you map VI to WK, that means you're changing. If you're looking at the adjacency matrix, you're changing both the row and column. Okay, the ith row becomes the kth row in the second matrix, and the ith column becomes the kth column because you've interchanged those. So you're doing matrix transformations, and I just want to do very simple matrix stuff here. We're not going to do the fancy stuff. Okay,
That's fair. Yeah.
Very basic.
Thank you.
Okay, good.
Yeah, that makes sense.
All right, good. Anybody else have a question?
I have a question about proving or disproving isomorphism.
I'm sorry, I can't hear you.
Can you hear me?
Faintly. So you have a question about
disproving isomorphism. Sorry about
Yes.
the volume. I don't know what's going on.
Now I can hear you okay.
Oh, okay, great. We've seen several ways to disprove isomorphism in like the pre-lecture material with
Yes.
Euler's formula versus
Yes.
first theorem 7.7. In the homework, I've got myself in a situation where none of those strategies seem to be applicable to the graphs that I'm trying to show aren't isomorphic to each other. Is there some generic way to show that two graphs are non-isomorphic besides like pointing to different numbers of edges or things like that?
It's easier to show something isn't isomorphic. Those are the ways you know those properties about the same numbers. You're saying the structure is the same, okay? So that all structure has to be as the same. And it's easier to show, for example, that some part of the structure is different to show it's not isomorphic. So if all of those things are the same and all the connections, remember the definition, an edge, if and only if, and then you go through that, and if you can show that, then it's isomorphic, and if you can't show it, then they aren't.
Is there I guess I'm struggling to find a rigorous way to show that there is no such isomorphism, like that one doesn't exist.
You want to show there doesn't exist one.
To show that two graphs aren't isomorphic, yes.
Well, you know, the properties of the same number of nodes, the same number of edges, the same number of cycles, the same lengths of cycles, and then just the straight mapping. You know, if you can show there's an edge between two things in one graph and not in the other, then not in their images in the other, then that's a way that says they're definitely not isomorphic. But it goes back and forth. That's if and only if, and you have to go straight back to the definitions. We haven't covered a lot of other fancy things, so I don't want to go super fancy. You should be able to do that using the theorems and proofs that we had about isomorphisms. Let me go back here. We didn't have that many theorems related to isomorphic graphs. We had that if they're isomorphic, then they have a lot of properties. And then we have if they're planar, there are a bunch of things we know about. And we have Euler's theorem. Basically, to weigh, if you're looking at planarity, if any of the things that we know, when we say if something is planar, then it has certain properties. Then if it doesn't have any of those properties, then it can't be planar. That's a contrapositive. Okay.
guess I'll just look for.
So
Just another book then.
basically what you have to say is, look, for any mapping, if they don't have the same number of nodes, you're done. They're not isomorphic. They don't have the same number of edges. You can find, in any kind of a mapping, how do you do that? That's one way, and it's a very straightforward way. Oops.
Okay.
Okay, I'm sorry, I have to go now. All right.